Good morning, everybody. I am Vempati Srinivasulu, Assistant Professor of Chemistry, Nagarjuna Government Degree College, Nalgonda. In the previous classes, we have learned about prime amines. What are amines? What is the classification of amines? What are primary, secondary, and tertiary amines with different examples? And a naming method. Two methods we discussed: common naming system and IUPAC naming system. Then followed by preparation of amines. So we have discussed different methods to prepare amines. One is ammonolysis of alkyl halides. Second, reduction of amides. Third, Gabriel phthalimide synthesis. Fourth one is Hoffman bromide synthesis, and the fifth one is Smith rearrangement reaction. In the last class, we have discussed especially these three types of methods. In Gabriel synthesis, we use phthalimide. Phthalimide in presence of base with alkyl halide, it reacts. Nucleophilic substitution takes place by giving N-alkylated phthalimide. On hydrolysis, it gives amines. In this method, we can only prepare primary amines, the two aliphatic amines only. In the second method, Hoffman bromide method, it is proposed by and developed by Hoffman. In the during course of reaction, we come across a reagent called N-bromoamide. That's why it is Hoffman bromide reaction. In these reactions, amides are converted into primary amines. In this method, we can prepare aliphatic as well as aromatic primary amines. Okay, we will study the mechanism and with examples we discussed. In the third method, Smith reaction. In the Smith reaction, acids are converted into amines. Okay, carboxylic acid in presence of concentrated sulfuric acid, when it reacts with hydroxylic acid, it gives different intermediates, and finally it gives primary amines with carbon-less. This is a Smith reaction. We have discussed mechanism and with different examples. Okay, now today we start today's class. This is for BSc second year, third semester students, amines part 3. Okay, so in this class, what topics we are going to discuss? One is physical properties of amines. Second, use of amines, ammonium salts or amine salts as phase transfer catalysts. Very important, PTC. Use of amines, ammonium salts or amine salts as phase transfer catalysts. Then followed by chemical reactivity, we have different chemical methods. In this session, we discuss only basicity of amines, alkylation and acylation. So these are the topics we are going to cover. Next. Okay. Okay. Coming to the physical state. Amines with lower carbons, they exist in gaseous phase. Whereas 3 to 4 carbons, that means propylamine 2 and butyl up to butylamine, these exist in liquids. When the number of carbons in R is increases, they exist in solids. So lower carbon, lower amines means methylamine, ethylamine, like that. There exists a gaseous state. Remaining, as the number of carbons increasing in R group of amines, they become liquids, and finally with higher molecular weight or solids. Generally, these are colorless, and when they are exposed to atmosphere, time being, they will become some color. They get some color. Especially aniline. Aniline is a colorless liquid. It is on exposing, it will undergo atmospheric oxidation by giving brown color. So amines as such, they are not colorless. On atmospheric oxidation, they will give different color. They get colors. Then the amines gives fishy odor. Fishy odor. Coming to the solubility. Okay, coming to solubility, when we compare primary, secondary, and tertiary amines, so primary and secondary amines are soluble in water. Increase in size of R group. That means in RNH2 amines, the formula is RNH2. R means alkyl group or aryl group. Generally, we discuss about aliphatic. The number of carbons increases, solubility decreases. So primary and secondary amines are soluble in water. Why these are soluble? Because of they form hydrogen bonding. You know what is hydrogen bonding, how it forms, we will discuss, we know already. So due to hydrogen bonding formation, primary and secondary amines are soluble in water, whereas tertiary amines are insoluble in water. Generally, amines higher number of carbons increase in alkyl group, they become hydrophobic. So this hydrophobic nature amines doesn't dissolve in water, like polar solvents. They dissolve in organic solvents like ethyl alcohol and benzene, ether, etc. Okay, so coming to the boiling points. So when we compare the boiling points, the primary amines are having more boiling point than secondary. Secondary amines are more boiling point than tertiary. This is due to same thing, because of having intermolecular hydrogen bonding, the molecules get attached, get clustered, get assembled. So due to this aggregation, it requires more amount of energy to break them into gaseous phase. The boiling point is a temperature required to convert liquid phase into gaseous phase. So when these primary and secondary amines, they have internal molecular bond, intermolecular hydrogen bonding. Due to this bonding, they are stable and they doesn't want to go into vapor phase. That's why if you want to convert into vapor phase, it requires some more amount of energy. That's why these are having more boiling points. When we compare to secondary and primary, primary is having more boiling point. Why? Because number of hydrogen bonding is more. So based on number of hydrogen bonds, the boiling point varies. In the case of tertiary, there is no question, there is no hydrogen bond formation between the same molecules. That's why these are having less boiling point when we compare to primary and secondary. So these amines, especially aliphatic amines, are aliphatic amines, aromatic amines, aliphatic amines. The molecular weight, it depends upon molecular weight. Then when we compare with the alcohols and hydrocarbons, alkanes, so these boiling points of these substances are in between. So already we know that alcohols are having more boiling point due to strong hydrogen bonding, due to oxygen is more alternative. That's why the tendency of formation of hydrogen bonding is more. That's why alcohols are having more boiling point when we compare to amines. Coming to the alkanes, there is no question of formation of there is no formation of hydrogen bonding. That's why in alkanes we don't observe any hydrogen bonding. Due to this lack of hydrogen bonding, alkanes are having lesser boiling point. Where all these are comparisons with in comparison to the compounds with the same molecular weight. Molecular weight changes, generally higher molecular weight compound having more boiling point. That's different. We are comparing alcohols or amines or alkanes having similar molecular weight. So generally alcohols are having more boiling point than amines, and amines are having more boiling point than alkanes. This is due to hydrogen bonding nature of amines and alcohols. So these are the different um, what these are the some physical properties about our amines. Coming to the next. Okay. So next point. Okay, what is this? Use of amine salts as phase transfer catalyst. Phase transfer catalyst. You see, what is phase transfer catalyst? And what are the examples, different examples of phase transfer catalyst? And what is the mechanism is going on? Is this phase transfer catalysis? Actually, what is the definition of phase transfer catalyst? All these things we will discuss one by one. So first of all, quaternary ammonium salt. So, for example, tetrabutyl ammonium chloride. You see this one. R N R4 N plus X minus. This is a one example for tetraalkyl ammonium halide. So these type of ammonium salts acts as phase transfer catalyst. So not only this, you see this quaternary ammonium salt, quaternary phosphonium salts, crown ethers, and kryptons. These are the new compounds, kryptons also. So all these classes of compounds act as phase transfer catalysts. So let me define what is a phase transfer catalyst. It is a catalyst that facilitates the migration of a reactant from one phase to another phase where reaction occurs. Very listen carefully. PTC, phase transfer catalyst, is a catalyst when it facilitates, when in a reaction, it is in the presence of this catalyst in a reaction, it facilitates migration of one reactant or any reagent from one phase to other phase. What are these phases, and why they have to carry this why we have to use this phase transfer catalyst, and what is the mechanism, we can discuss, we can discuss. So for example, tetraalkyl ammonium halide is a one type of example for phase transfer general formula. For example, in the place of alkyl, tetrabutyl, this is you see this one is tetrabutyl ammonium bromide, or tetrabutyl ammonium chloride, or tetrabutyl ammonium nitrate. All these are examples for phase transfer catalysts. So what is happening here is transfer of inorganic ion from one phase to another phase. So in there are some reactions. If without this phase transfer catalyst, the reaction doesn't. If you provide all the required things, reactants, reagents, temperature, but reaction doesn't proceed. So why? This is we'll discuss in the mechanism. Okay. Okay. You see, there is a one reaction. You observe carefully. You see this one. What is this? Bromooctane. So it number carbon, long chain hydrocarbon. It's bromooctane. Bromooctane, when reacts with sodium cyanide, for example, the reaction is this compound is not present. You assume. So reaction doesn't proceed. So what is happening here? Sodium cyanide is a aqueous phase, whereas this bromooctane is organic phase. It's a non-polar substance. Substrate is non-polar substance, whereas reagent is another reactant is sodium cyanide is a aqueous. So polar phase, polar substance is a non-polar. So when we mix these two in a reaction vessel, they don't come close to reaction occur. Why? Because these two are different phases. One is the aqueous phase. In the aqueous phase, we have sodium cyanide because of ions, Na plus and Cl minus. These are ions. Generally, these are soluble in the aqueous phase. Water. They don't dissolve in organic solvents or non-polar solvents like ether or anything. So this bromooctane, because of octyl group, is a long chain hydrocarbon because of its hydrophobic nature. These are soluble in only organic solvents like non-polar solvents like ether or benzene, etc. So that's why when we combine these water soluble sodium cyanide and organic solvent soluble in bromooctane, when we add these in a RB flask or any reaction container, they don't come across, they don't mix properly. So reaction doesn't, without having collisions, there is no question of reaction, we know. So that's why if you see, if the presence of just we add the reaction, if you add this one, what see this one, tetraalkyl ammonium halide, the reaction proceeds within completes within 1 or 2 hours with giving 92% yield. See, this is very important. Reaction yield is 92%. What is the product? You see, this is the product. uh, Octyl cyanide, cyanooctane, octyl nitrile. Okay, so what is happening here is a nucleophilic substitution reaction. If you see the co-reaction carefully, what is happening here? This bromide is leaving as Br minus. This cyanide is attacking on this. So cyanide is coming, replacing this bromide. Bromide is going as Br minus. It's a nucleophilic substitution reaction. So to occur this nucleophilic substitution reaction, so we require this type of catalyst. What is this? Phase transfer catalyst. You see, this is a tetra. So if you observe the ionic structure of this compound, molecular structure of this compound, you see N is plus charge. All four groups are this one, this one, this one, these four alkyl groups are hydrophobic in nature because of having high long chain carbon, and halogen is ionic. This N plus and X minus are ionic in nature, and R groups are hydrophobic nature, hydrophilic. So both hydrophilic and hydrophobic groups are present in that reagent. That's why it is soluble in both parts. It is soluble in organic solvent as well as aqueous solvent. So when we add this reagent to the substrate, what happens? It because of solubility in both phases, so it easily goes to the sodium cyanide, and easily this compound tertiary butyl ammonium halide is converted into tertiary butyl ammonium cyanide. When this cyanide is already, it is also bipolar nature. That means hydrophobic nature and hydrophilic nature of cyanide. That's why this is goes to the from aqueous phase to organic phase, where alkyl halide is dissolved in organic phase. So when these are come together, the reaction proceeds. Nucleophilic substitution reaction occurs, and the chloride or bromide is substituted by cyanide. So our product is obtained. So this is a reaction. So this is one reaction. So octyl cyanide bromide bromooctane, when reacts with one bromooctane with sodium cyanide in presence of this catalyst, PTC, phase transfer catalyst. It is a catalyst. It is transferring. It is doing a migration. It is migrating from aqueous phase to organic phase, or organic phase to aqueous, wherever the reagent is required. It due to its solubility in both phase. So this is one example. One more example is that you see alcohols. Alcohols on reaction with alkyl halides, this reaction also doesn't proceed without this reagent. If you add this reagent, reaction goes considerably, giving good yield of ether. Okay, it's a Williamson synthesis like example. So alkyl halide with alkyl, okay, not Williamson synthesis. Okay, this is a synthesis of ethers. So coming to the one more compound, one more reaction, alkene. double bonded hydrocarbon. When reaction with the potassium permanganate, it undergo oxygen reaction by giving carboxylic acid with one number of carbon less. So this is also we have two phases. Potassium permanganate is a aqueous phase, whereas alkene is a organic phase. So to mix these two, to KMnO4 come close to the organic phase, we have required a phase transfer catalyst. So these are the different examples for phase transfer catalytic reactions. So we see the mechanism. What is happening in the mechanism? We'll see. C is a reaction container. You see, you can carefully observe. There are two phases we are observing. You see, this is the one. This is the interface. So above phase is organic phase, below phase is aqueous phase. So above below are different depending upon the density of the substances. More density compound comes down, and lower dense compound comes upper phase, upper side, above phase. So in this case, organic phase is above phase, upper medium, and aqueous medium is below, lower medium. So in the alkyl halide, if you take an alkyl halide, it is soluble in organic phase only. It doesn't goes to the aqueous phase. Whereas our reagent sodium cyanide is soluble in the aqueous phase. It doesn't go as such to the organic phase. That's why reaction doesn't proceed without adding any phase transfer catalyst. If you add this phase transfer catalyst like tertiary butyl ammonium halide, what happens? It goes to the aqueous phase and react with the cyanide, and it converts into it converts into this one, tertiary butyl ammonium cyanide. This is also same hydrophobic and hydrophilic nature of the both parts. It moves to the organic phase where alkyl halide is available. So this reacts with this alkyl by converting into alkyl cyanide. When it goes to the this phase, the reaction proceeds. Why? Because these two reactive molecules are colliding. So come closer. That's why reaction proceeds by giving alkyl cyanide. So this is the mechanism. So what is the function of this reagent? Phase transfer catalytic reagent is, it is the function of this is migration of ionic reagent from aqueous phase to organic phase to reaction where the reaction to occur. So this is the, so when the reaction proceeds and gives the products. So this is the phase transfer catalyst mechanism. Catalysis, phase transfer catalysis. I think you understood. Coming to the next slide. Okay. Chemical reactivity. So what is chemical reactivity? Generally, we discuss in this our syllabus, we have some basic nature of chemical reactivity and alkylation and acylation and carbylamine reaction. So different reactions we have. So we will discuss one by one. So what is in the chemical reactivity? Generally we will discuss basicity. So these amines are having basic nature. So in definition, what is a base? When amine reacts with water, it is giving ammonium ion, ammonium ion and hydroxide. The compound which provides hydroxide ions in water is called base. That's all. So that's why it is base. One more amines with acid H3O plus, it is giving ammonium ion and water. This is also an example. So these two reactions telling us amines exhibits basic nature. So what are the bases? We can define basicity as per Bronsted-Lowry theory as well as Lewis theory. So the amines, basicity of amines explained by these both theories. Electron pair donor is Lewis base, whereas proton acceptor is Bronsted-Lowry base. So we can explain these two in this. So ammonia amines when attract protons. So attracting proton, accepting proton is a basic nature. So you can say it's a base. Okay. At the same time, it is donating electron pair to the proton. That's why you can say Lewis base. Okay, this basicity is expressed in terms of Kb and pKb. We know that. We could write the Kb equation. You see, this is RNH3 plus X minus concentration and OH minus concentration by RNH2 concentration. So we need not write water molecule concentration. That is very high when we compare to this. It is okay. Then basically, generally we can express the basic nature in Kb values. Kb value is more basic, and the Kb value is proportional to the basic strength. Whereas the pKb is equal to, what is pKb? pKb means logarithm minus negative logarithm of Kb values. pKb value increases, basic decreases. pKb value decreases, basic nature increases. So lower the pKb value, more basicity. So okay, so when these amines are reacts with HCl, they convert that corresponding aminium salts. These aminium salts are regenerated when we add NaOH to the. So we can dissolve in acid. That means amines are soluble in acids. These dissolved amines are regenerated by adding NaOH. This is a very important point to be noted. It is useful in the separation of amines. Okay, so this is something about basic strength. Okay, we compare this basic strength with the different classes of compounds. So basicity, okay, then to explain basicity, we have three factors: plus I factor, plus I effect, and steric factor, and solvent effect. So we'll discuss one by one. So when we compare primary and secondary and tertiary amines, primary amine, secondary amine, tertiary amine. So as per plus I effect, so electron donor is a base. So when presence of alkyl groups are plus I groups. So electron releasing groups. So more number of releasing groups, electron ability is more on nitrogen. Thereby they easily donate electron pairs to the protons. They accept easily proton. That's why basic strength increases. So more number of alkyl groups, stability increases. Further, in the alkyl group, more number of carbons, it also increases basic nature. So, in general, so primary is less than secondary. The order in gaseous phase, primary is less than secondary, secondary is less than tertiary. That means tertiary amines are more stronger bases as per inductive effect alone. Okay, coming to the next point. Steric factors also plays key role. So why electron pair availability is important. So the due to tertiary amine, its crowdiness is increased. You see, observe carefully. In tertiary amines, N is flanked by three different alkyl groups. So H, H, H. So due to this steric nature, proton cannot attached to the nitrogen, or electron pair doesn't can not easy to donate to the proton. In other words, that's why donation or acceptance of proton will be decreases. But because steric nature of the bulky groups, the attacking of proton to the nitrogen becomes less. That's why, as per steric factors, this is the order. Secondary is more basic than tertiary, and tertiary is more basic than primary. So in secondary, we have two alkyl groups, as well as somehow bulkiness is very less. But in the primary, there is no steric factors, but plus A effect is very less. So this is a order. Secondary is more as per steric factors, whereas in the primary plus A effect, tertiary is more stronger basis than primary. So we have got we have one more point to be discussed, that is the solvent effect. Okay. Okay. So in general, okay, I think no, one more slide you missed. Okay, salvation. So in terms of aqueous mechanism, especially this is applicable to aqueous phases. Due to solvolysis, when primary means ammonium salts. So one thing we have to be noted. So whenever our RNH2 is attached to proton, if you form RNH2 plus, I forgot one thing, RNH2 plus. So when amine abstracted proton, it forms ammonium ion. So stability of this ammonium ion is important. It is more stable stronger base, less stable, weaker the base. So we can, when we come to the comparison of basicity, we have to assess the stability. Should be more stable, it is that means it implies that it easily protonates electron pair. That's why stability, we have to assess the basic strength. We compare the basic strength on the basis of stability of these ammonium ions or salts. So this is the thing. So coming to this, so ammonium ion in the place of for primary compounds, it is having three hydrogens. When amine compound protonated in presence of acid, it forms ammonium salt, ammonium ion or salt. This ammonium ion or salt having three hydrogens, R N H 2 plus one more H. That's why these three hydrogens are surrounded by solvent water. That's why due to hydrogen bonding, there's a three hydrogen bonds are there. So hydrogen bonds are three bonds are there. That's why more stable. When we compare to secondary, we have only two. In the tertiary, only one. That's why number of hydrogen bonding is less. And when we compare, this is OH2. So okay. So tertiary amines are lesser stable due to less number of hydrogen bonds with water. That's why. So by comparing on the basis of solvents, we can say that we can compare the basic strength of different amines. So as per this theory, solvents is primary amines are more basic than secondary. Secondary are more basic than this is the order. You see, this is the order. So whenever we come across to compare different amines, we have to consider all these things. We have to consolidate all these things. As per electron releasing theory, inductive effect, tertiary are more stronger bases. And as per the steric factors, secondary is more basic than tertiary. As per the solvent, when the aqueous phase, primary amines are more stronger bases. So by comparing these three issues, we come to a one outcome in general. So whenever in the case of methylamines, so lower amines, so secondary is more basic than this is the order. This is the order in general. In the case of methylamines, so secondary methylamine is more stronger base than primary. Primary is more stronger than tertiary. This is in the case of only primary amine, less number of. When the case of second ethylamines, you see more number of amine, not only ethyl, maybe amines with more number of carbons in alkyl groups, ethyl, propyl, like that. So this is the order. Secondary is more. Secondary is more. In the both cases, secondary is more. But in this case, tertiary is more stronger base than primary. In this case, primary is more stronger than tertiary. So in both cases, secondary is more stronger base. This is the basicity of amines. Coming to the chemical properties, alkylation. So what is alkylation? When amines are react with alkyl halides, they'll give different alkylated products. Secondary amine, tertiary amine, finally ammonium salt. So what is happening in this reaction? So in each step, one hydrogen is replacing by alkyl group. So actually it's a nucleophilic substitution. In the net reaction, the number of hydrogens are sequentially stepwise undergoing substitution by alkyl groups. This is alkylation. So when amines are reacting with our primary amines or any amines, we'll take primary amines. Amines, when primary amines are reacting with alkyl halides, they will give alkylated products. And then N-alkyl, I mean NN dialkyl, I mean like that, and tertiary trialkyl amines like that. So this is reaction is known as alkylation. So what is the reaction is going on? What is the sequences? So you see, this is amine. Amine when react with alkyl halide. So halide is X minus electron bond due to more electronegativity. X becomes X becomes more X minus delta minus, R becomes delta plus. It's a electron deficit carbon. So due to electron deficiency, electron pair is available on nitrogen. When they combined, they are added in the vicinity. Electron pair amine to electron pair donates. This amine electron pair donates from alkyl group to amine to alkyl group. At the same time, this X goes as X minus. So what is happening here is we are getting a salt RNHR, RNH2, R2NH, R2NH2X plus minus. So halide salt. So what happened here? This alkyl nitrogen pair on nitrogen is given to the alkyl group. At the same time, it formed a bond, N alkyl, N carbon nitrogen bond. So after this halide ion is more having strong base, conjugate base. It abstracts proton from here and becomes already N is having plus charge. This bond pair electron moves towards nitrogen because N plus is unstable. Nitrogen with plus charge is unstable. It can't bear plus charge. Being highly electronegative, it attracts the electron pair from nearby hydrogen. Thereby hydrogen goes as H plus. This HX goes as HX. That's why we are getting this secondary amine. N alkyl amine. N dialkyl amine. So there is one more electron pair on still there is an electron pair on nitrogen. It reacts one more alkyl halide giving secondary amine. This second tertiary amine. So primary amine gives secondary amine. So let us primary amine giving secondary amine. Secondary amine giving the same reaction with tertiary amine. Tertiary amine finally it adds to the alkyl halide. There is no hydrogen. That's why addition reaction takes place. By combining this alkyl amine and alkyl halide, you get tertiary quaternary ammonium salt. That's a different thing. So what is alkylation? In this course of alkylation reaction, hydrogens are replacing by alkyl groups one by one. This is alkylation. It is a nucleophilic substitution reaction. I think you understood. Okay, next slide. Okay. Oh, one more slide. We have. Okay. We have some examples. Okay. This is all. Okay, we have different examples. You see, one more example here, I forgot. This methylamine react with methyl bromide is giving dimethylamine, trimethylamine, tertiary ammonium salt. It's example. If you take ethylamine with methyl bromide or ethyl bromide, you'll get dialkyl, trialkyl, and tertiary alkyl ammonium salt. Is an example for alkylation reaction. Coming to the next slide. Okay, acylation. We have acylation syllabus. What is acylation? What is alkylation? Alkyl group is replacing hydrogen of amines. In the same way, acyl group. What is acyl group? RCO group. So this RCO group having compounds acid halides, esters, acidonates. All these three types of compounds, when they react with the amines, they easily gives acylate N-alkyl amides. What is happening this here in this is in the amine, one of the H is being replaced by acyl group. That's why it's called acylation, as in the alkylation reaction. In alkylation, what happened? Number of hydrogens are easily replaced by alkyl groups. In this case, hydrogens are being replaced, getting replaced by acyl groups. What is the source of these acyl groups? Acid halides, and esters, and anhydrides. All these three compounds act as acylating reagents. Okay, so what is the reaction? Amines are converting into amides. So this is a acylation reaction. So we'll discuss one example. You see, in this example, you see this example. What is happening here? This is a primary amine. This is acetyl chloride, acid halide. You take acetyl chloride or acetyl bromide, anything else. So anyone. So what is happening here in the presence of acid halide? So no reagent is required. Because of its reactivity, reaction happening without any catalyst. So this electron pair is there. The base it attract. Okay, this we can see the mechanism. So this is one reaction. So one more reaction, same ethylamine. You see this is the ethylamine with acetic anhydride. One SL group is replacing one of the ions of methylamine. That's why we're getting N-ethyl acetamide. This is N-ethyl acetamide. In the previous class, it is N-methyl acetamide. It is N-methyl acetamide. It is N-ethyl acetamide. The difference is ethyl group, alkyl group. So one more example, you see this one. So methylamine on react with ester or COOR. So in this ester also we have some acyl group. So acyl group is replacing one of the iodos. That's why you are getting this compound. What is this? N-methyl estamide. N-methyl ethanamide or estamide. These are the I base names of different compounds. So this is what is this? Acylation reaction. In acylation reactions, amides react with acylating reagents like acid halides or acid anhydrides or esters. They give corresponding acylated amines, nothing but amides. You see the mechanism. What is the mechanism? It is also like similar to alkylation. So amine is having electron pair on nitrogen. It acts as a strong nucleophile. So nucleophile, this electron pair gives to this carbon. Why this carbon? Because of oxygen, it carbon becomes more electron deficient. Because of oxygen electronegativity, the pi bond electrons pulled towards oxygen. That's why carbon becomes electron deficient. That's why an electron pair having nitrogen attacks on this carbon by giving this type of ion. So minus charge comes back. At the same time, X is goes as X minus, because this acidity is very reactive when compared to the anhydrides or esters. Why? Because X is the best living group. The nature of the group is very good living group. That's why the reaction proceeds at a considerable rate. So after this X minus attracts this proton by giving uh, finally amide. Very simple. Once again, I repeat, amides when they react with acid halides on nucleophilic cation and carbonyl carbon, it forms this type of ions. Due to electron pair delocation from oxygen to carbon, this X goes as X minus. We are getting this hydro plus N plus charged species. This X minus attracts hydrogen from nitrogen. Why? Because N with plus charge is unstable, and nitrogen attracts bond pair of one of the hydrogen. That's why H goes as H plus. The H plus is attracted by X minus, loss of HX plus HX. So HX is H is goes as HX by giving this type of amides. This is one mechanism. So one more mechanism you see from anhydrides. So when amines are react with anhydrides, so these two acyl groups are same. Both carbonyl groups are similar, because these two are groups are same. That's why any cardinal group can attack by attacked by electron donating amino group. So by forming this type of anion, electron pair coming back to the carbon. At the same time, this group is going as RCO minus. This RCO minus subtract this proton after by giving this secondary amine, that is amide, along with the acid. So this is also similar to the alkylation. In the alkylation, R groups attacks on carbonyl carbon. In this acylation, acyl group attacks on acyl carbon. Okay, amine electron pair attacks on nitrogen attacks on carbonyl alkyl carbon in of alkyl halides. In this acylation, amino group attacks on carbonyl carbon of acyl group. In these both cases, X is goes as X minus. In this case, RCO group goes as RCO minus. This RCO minus is a conjugate base, strong base. It easily accepts proton from the amine ion. Thereby, it is giving by giving our product amide. This is the mechanism for acylation. Okay. So this is the today's topics. What we have learned today is one, physical properties of amines, followed by phase transfer catalysis of nature, phase transfer catalytic nature of alkyl amines, especially tertiary butyl alkyl ammonium salts. What is phase transfer catalyst? How it works for different compounds. Then we discussed alkylation reaction with mechanism, followed by acylation reaction with examples and mechanism. So this is today's class. Thank you very much.